Hi there, my name is Miss Townsend and I love math. Welcome to Math with Townsend. This video is for advanced function students who are studying for the exam. It's a video that I requested because it was pointed out to me that on the review package solutions, I had made an error in one of my solutions. So I posted a PDF of the correction, but to be sure that the correction is seen, I'm going to make a quick video just explaining how this question works. So, to make a quick video, I have just scanned in my answers. So this is the question that started with an inequality of polynomials, which we turned into a simple polynomial inequality, where we have a third degree polynomial, and we want to know for what values of x is that polynomial greater than or equal to 0. So we need to factor. So I started using the factor theorem, so I assigned f at x equals and gave it that polynomial, and then I started taking factors of 120 and seeing what would give me a remainder of 0, and I discovered that f at 2 equals 0, doesn't equal 0, my bad. F at 2 equals 0, and therefore I know that x minus 2 is a factor. So again, that's using the remainder theorem and the factor theorem. So once I know that x minus 2 is a factor, I can use it to divide and find another factor. Now I did long division, you're certainly welcome to use synthetic division, but when I divided f at x by x minus 2, I get this quotient, and of course remainder 0, because I know it's a factor. So now I can write that f at x, instead of this cubic that we had originally, it's now this x minus 2 binomial, and then this quadratic. So now I need to factor that quadratic to continue factoring. So again, here's the binomial and the quadratic. So I'm going to define a new function, g at x, to be that quadratic, and factor it. So I common factored 3 and factored it. And in case you're wondering, it's right here that I made my error in the original solution. So I'm comparing, and I don't know why you would. Anyway, so I factored completely g at x. So if I put back in the other factor, this is now f at x, the original function I had, fully factored. And so now, instead of saying this cubic function in standard form, greater than or equal to 0, I will put it in factored form. It's the same function, but when it's factored, I can actually now do the next step. So our goal is to find what values of x would make this polynomial, or this left side of the equation, greater than or equal to 0. And we have two methods in the polynomial world for doing that. One is to make a graph, and one is to use a testing table. And I'm going to show you both solutions. So in order to graph it, we know that f at x is positive leading coefficient, third degree. So this is what it would look like on a graph. And it has roots at -4, 2, and 5. And so if I attach this shape to those roots, I end up with this function. And again, I'm not trying to make a beautiful function. I just need to see where is this function above or equal to 0. And so I've emphasized it there. So between -4 and 2, including both of those roots, and then after 5, and of course you can answer that in interval or set notation here and here. If you don't feel like graphing that polynomial, you could have made a testing table. So here's what the testing table would look like. So because my roots are at -4, 2, and 5, then my testing table has these 4 big regions. Between -infinity and -4, so I'll use -5 as my test. Between -4 and 2, so I'll use 0 as my test. 2 and 5, so I'll use 3. And then between 5 and infinity, I'll use 6. So here are the factors. I haven't included the constant 3. Remember, it was 3 times x minus 2, etc. And I haven't included 3 here because 3 is a constant that's positive, so its polarity doesn't need to be acknowledged because it's positive, so it's not going to affect the polarity. So when I test each of these little binomial pieces, if I sub -5 in, I get a negative. If I sub 0 in, I get a negative. If I sub 3 in, I get a negative. If I sub 6 in, I get a positive, and so on. And when you look at the end results, so for example, in this region between -infinity and -4, a negative times a negative times a negative makes an overall result of negative. So that's not what I'm looking for, because I want greater than or equal to 0. And so I end up discovering that this region and this region are positive, meaning above 0. So that's between -4 and 2, and between 5 and infinity. And of course I need to include my roots, so again, between -4 and 2 inclusive, and then from 5 to infinity including 5. Okay, so I hope that was helpful. Sorry for the original error.